So let's begin our afternoon session. So before we get started, apparently there's at 4 o'clock there's going to be an additional optional lecture. So after this lecture, following a break, and I'm told that's an experimental thing. I wasn't told much about it. Maybe it's a session on kind of discussion of several different experimental tools. But I'm not really sure. If somebody organizing that wants to say a word or two about it.
It's mostly on scan probe techniques at this point. Called it visualizing quantum matter.
Great.
Okay, great.
Thank you. Right. That's the information I didn't have. Okay, wonderful. So with that announcement, it's a pleasure to introduce Xiao-Gang Wen from MIT. So Xiao-Gang is going to tell us about topological order, both some specific examples and the general theory of topological order. Thanks.
Thank you. Yeah, it's a great pleasure to come here and so see those really bright students here. And so in my full lecture, I basically plan to talk about some example of topological order and which leading to some general theory of topological order with the symmetry or with the fermions, things like that. And so the first question is that we know that this the Landau symmetry breaking theory does not explain all the possible phases, And so the naturally one asks, why is that, And then one asks, for those phases which cannot be described by Landau symmetry breaking, what do they look like? What kind of a situation are we in? So we will first try to say that. Then what do you mean by the phase? And what is a phase really means? So here in condensed matter, we study so-called local system. I think Nick Reed have explained that the local system means that the Hilbert space is a direct product of a small Hilbert space which live on each side, and we have an interaction which only in the Hamiltonian which only interact among a few neighboring sites and things like that. And then in my lecture, I mainly concentrate on the state with energy gap. But however, the state with energy gap is a concept of thermodynamic limit, because for any finite system, every state have energy gap. There's no gapless states. So by thermodynamic limit, it really means that we have to we are thinking about a sequence of a Hilbert space and Hamiltonian. And where the size of a system, which n is the size of system, n go to infinity. So actually, mathematically, we are not talking about the particular Hamiltonian. We are talking about a sequence of Hamiltonian in order for many concepts to make sense. Okay. And there's another thing that, as a sequence go to infinity, then the spectrum looks like this, where this energy gap remains finite as n go to infinity, but however, this splitting may go to 0 as n go to infinity. And so that's a situation we're considering. So the typical gapped system have this kind of energy spectrum. And so even ground states became tricky concept. So actually it should be called a ground space. These two states span a subspace, we call the ground state subspace, and that represents a low energy manifold of the system. And then what is a phase? Well, the phase is just equivalence class. So when you have a two sequence of a ground state or ground space, and then there is some equivalence relation. You say, so these two sequences are equivalent. And then when you have this equivalent class, then the equivalent class will become a phase. Phase just means equivalence class of a state, or equivalence class of this sequence. And one obvious way to do the equivalence relation is so-called local unitary transformation. That's one of the important concepts. Now we say that two states are equivalent if they are connected by local unitary transformation. The local unitary transformation is something like that, where you have a unitary operator act on the nearby sites. And so you can have one layer of a unitary operator act on these patches. You may have another layer of unit transformation, and then those transformations would change a state to another state. But however, if the sequence are connected by local unitary like this, then we say these two sequences are equivalent. They belong to the same phase. If two sequences cannot be connected by local unitary, then we say they belong to different phase. So that's we try to define what this phase really means. Okay, so that's it. So that's how the phase was defined. Yes.
Is it guaranteed, for example, for the first few members, you can have this local unitary transformation that all the following up members in two series would automatically have this?
No, it's I think you do require this local unitary relation for every n. Okay. You know, that's however, there's one drawback in this picture. You know, what do you mean by the system with size n3 or n4? The sizes are different. And you know, usually if you have a translation symmetry, then enlarge the system is very natural. You just enlarge the system, just adding a few sides. There's a natural way to do so. But however, if you don't have a translation symmetry, it could be that for n3 is a ferromagnetic state, n4 is anti-ferromagnetic states. There's nobody prevent you to do that, you know. So for the one who really be careful, then say this is nonsense, you know. It could be the half system in the ferromagnetic, other half anti-ferromagnetic. This all kind of combination is possible, you know. So this just doesn't make any sense actually, although the paper is published. So actually, what is missing is that there's another ingredient here to define this. If you have a translation non-invariant system, you need add another ingredient. You have to find a way to connect the system with different size. And how to do that? So one way to do that is to add in the product states. Suppose you have a system with one size. You add the products like just all spin-up states. That's changing the number of lattice sites. So now when adding these product states, now the system size is same as the next system size. Then these two with the same size are connected by local unitary. So this is like a generalized local unitary, where in addition to local unitary, we also add or dissolve a product state into it, so that we can change the total dimension of a Hilbert space, a number of sites. So therefore, this is generalized local unitary connecting the system with different size. Then, yeah, this is a better picture. So then we have so this kind of equivalence relation would define the phase. Okay, so this is one of main message. So the quantum phase defined here require this is almost like an RG. Means the system with different size, you can reduce the size system like doing cross screening by throwing away some product states. So somehow the system have this property. It can change the size by throwing away some product states. And this is very, very important. And so with this, then we basically have this definition of quantum phase. And this property, the ability to dissolve the product states, is the meaning of a liquid. So the states which can dissolve the product state into it seamlessly, those states we call liquid states. So that's what a liquid means. Any question? Yes.
Yeah, so it seems like I could just always sharply backward and taking out product states as much as I want.
Not always. Yeah, there's. I will see.
At some point where you have to stop and say I can't go any smaller, otherwise.
There are some states you cannot do even single step. You know, I will give you some example. So this is just here just emphasizing some equivalence relation between systems of different sizes are very important. And here we achieve that by adding these product states. That's the main message. Yeah.
When you add these,
That's very, very important. Exactly. Very, very important point. they should have finite density. It's not like you cannot have a delta function density, everything in one point. That's not allowed. And it's very important. The zero density is okay, but you do not allow to have infinite density.
Also, you don't want them to put them all along the edge.
Along the edge, maybe it's okay. Yeah, I think that's probably is okay, but you do not allow to have infinite density. So as long as density is bounded from above, at the moment, to be, these are just some kind of a physics idea. At the rigorousness of mathematical physics, I don't know whether some state should be modified. That's yeah.
I mean, if your system is finite size, aren't all
Very good. So that's something I'm hiding here. So the number of layers should be finite. Otherwise, if you do not have a bound on number of layers, then everything are connected. So there's no disconnect case. So here we say the number of layers is finite and uniformly finite regardless of system size. So no matter how big a system, I always need to have finite layer of unitary to connect the two. And certainly in this case, what do you mean by two systems are connected or are the same after transformation? It means they are locally the same. There's all kind of details. If two systems are locally indistinguishable, we say they are the same. And because the some limited can be tricky. Yeah. Yeah. The point is that we don't have connection between systems with different size. Local unitary only connect systems with the same size. However, when we take in thermodynamic limit, we make a system bigger and bigger. But we have to make them bigger in a certain way. Otherwise, a system in one size can be quantum Hall state. System in next size can be the Fermionic states. We should have something to control that. But in this case, we don't have any control of that. It could be that a system with different size and in different phase. Then this definition doesn't make sense. Yeah. So the trick to make systems with different size are connected is to say that they only differ by product states in some sense. Yeah. So that's we connect them together. Yeah. Here is a finite. We say that the Hilbert space on each side is a finite dimension. Yeah, this is a lattice system, and we view for continuum system there's there's an issue here. Here we just say we make assumption that the finite volume have a finite degree freedom, so basically we only do lattice. Yeah. Whether for continuum there could be subtlety because the things can hide at infinity energy. There can be delicate things. Yeah. So here I say nowhere to hide. Okay. So using this, actually we can define this concept of topological order or long-range entanglement. So basically, usually, suppose we have a system with no symmetry, gravity system with no symmetry. If using Landau theory, say there's only one phase because there's no symmetry to break. But however, if you think about entanglement, there could be several phases or many phases, because even though we have no symmetry to break, the system may have different entanglement pattern. And what I mean by entanglement pattern is really following. Suppose we have some state we call long-range entangled, which means we cannot connect this long-range entangled state to the product state via this local unitary or generalized local unitary. We assume this kind of state exists. So we say that's long-range entangled. So that means we have something different from product state. And so this will belong to one phase, this belongs to another phase. So at least we have something non-trivial. And but however, actually we have something more than that. For shorter entangled states means shorter entangled state are states which are connected to the product state by local unitary. then we can easily see that every two, any pair of short-range entangled states are connected by local unitary, almost by definition. So they all belong to one phase. So therefore, the state which connect to product states all belong to one phase. There's only one phase. But however, the states which do not connect to product states may belong to different phase, means they themselves are not connected by local unitary. So then under this different phase, we call the pattern of a long-range entanglement. So that's basically the definition of a long-range entanglement. Okay, and this basically is a topological order. This kind of a distinction is a difference in entanglement pattern is called a topological order. Certainly, historically, the topological order is introduced via the other method. But later, we understand the topological order really representing many-body entanglement, a pattern in many-body entanglement, but defined in this particular way. So in my lectures, I probably would I would basically concentrate on try to understand this kind of top phase, how to describe them, how to label them, etc. Yeah. That's right. Yeah, that's right. Because this, again, very important, because you only do gaped system. When you have gapless excitation, it may have a long-range entanglement. But yeah, actually, this is a very, very interesting question. How to bring this kind of concept entanglement to gapless system? Sometimes you have a simply gapless mode give you long-range entanglement. Sometimes the long-range entanglement due to more novel reason, and how to separate these two, I'm not so clear.
Also, if I had a thermal state, it would have false
entanglement. Yeah.
But surely it's not long-range entanglement.
Yeah, that's right. So certainly we know the quantum phase are defined even for gapless system. But so far, my definition only works for gapless system. And how to generalize this for gapless system would be quite an interesting topic. And I emphasize on liquid. So actually, here I assume we are doing quantum liquid states, means those states all can dissolve the product states. Actually, there are examples of non-liquid gap states. So what are those examples? Actually, it's pretty simple. So we heard of quantum Hall states, which are two-dimensional states. You just stack many layers of a quantum Hall state to form a three-dimensional gap states. These three-dimensional states actually is not liquid. You say why it's not liquid? It's pretty ordinary. It's a quite ordinary state. But actually, it's a fail. This dissolving product state fail this test, because for the system with a bigger size and more layers, and you cannot, if you want to make this, you cannot reduce the system size by squeezing out some product state, because no matter how many products you squeeze out, you cannot change the number of layers. Or another way to say, if you want to start from smaller system, you want to add a product state to get your bigger system, you can do that. But your bigger system have the same number of layers of quantum Hall state as your smaller system. So therefore, as you scale the system bigger and bigger, the number of layers remain the same, and the number of layers become more and more dilute. So it's not the ordinary thermodynamic picture of a layered quantum Hall states. So actually, layered quantum Hall states already have this property. It's not liquid. Yeah, and certainly you could have a layer in a stack in z direction. Maybe at the same time may have some stack in x direction or y direction. So the system may looks like pretty cubic, but still have a hidden layer structure. And also, when you have this property, the ground degeneracy can be infinite. For example, in this case, the ground degeneracy can be some m raised to number of layers, power of layers. It's very big, but also can be small. For example, in this case, if you have a boundary condition that this layer connect to next layer at this boundary, then the whole system actually only have one layer effectively. So ground degeneracy is just some final number. Or you can have a skipping one, so this effect has 2 layers, so m squared. So that's one sign of this kind of a non-liquid system. On the ground degeneracy for periodic system, depending on how you do the periodic boundary condition, the ground degeneracy can be changing wildly. You know. So there's one more novel non-liquid state. This has a cubic code. In the hash cubic code, basically, is on cubic lattice on every side we have a 2 spin 1/2. Okay. And they have 2 terms, gz, gx term. Okay. And these terms have they act on what this 8 side. They act on 8 sides. This 8 side operator. On each side have 2 spins, so this z and I, so zz. So this kind of tensor product, those operator is enter here. So gx is now is a similar thing but with x. So one can show that this water again is commuting projector. So this is exact soluble. So it turns out that this Hamiltonian is very strange. Depending on system size, the ground degeneracy can change wildly. It's a little bit like that, but not quite like that. So it's not obvious this one is a stacking 2D topology order. It's not a stacking 2D topology order, but it's something very strange anyway. So this kind of thing is what Liang Fu talk about is this topology order without anion. You know, these are different type of topology order or different type of thing. You know, and but basically it's not quantum liquid, not liquid. And I want to add one more thing is that these topology order have no quantum field theory. You know, people have an impression that the quantum field theory describes everything. So now we have an example there. This kind of a lattice model have no continuum limit, have no continuum quantum field theory to describe their low energy property. So they are really something beyond the quantum field theory. Or you can, using quantum field theory, if you allow infinite number of field. So if you really want to use quantum field theory, you may need the infinite number of field to describe those states. And okay, I don't know why, but I have an example suggestive for that. It's like this one. Each layer for quantum Hall states is a Chern-Simons theory. When you're stacking many layers, you have many Chern-Simons theory, and each layer have its own gauge field. So therefore, for this example, the number of gauge field is equal to number of layers. When the system getting bigger and bigger, that you require more and more gauge field. And this is intrinsic. You know, this number of gauge field are really intrinsic. So so through this example, that's why I say that you need infinite number of quantum field to describe this. Yeah, but this this is really from the stacking 2D system, so it's simple. But there are some more non-trivial things, and let me put it this way: when I'm making that statement, I think that statement may not be accurate and true, but closer to the truth. I mean, I don't think I misled you. That's you know, when I say something is beyond quantum field theory, certain people naturally ask, then what? What is beyond quantum field theory? So I'm thinking along the line, maybe you need an infinite number field, or maybe even that is not enough, or something even beyond that. So, but certainly this is kind of something new direction. It's a very, very interesting direction, you know. Yes?
So will you expect some what could be possible?
Probably not. I think all those states probably have a property that the local operator, all the local operators have short-range correlation. So by linear response, there's nothing in the linear response. I may say that too strongly, but yeah, I don't. Yeah, but the usually local operator have no probably don't have any feature in the local operator, local correlation function of a local operator. Maybe there's no feature there. That's my guess. Yeah. Yeah. Since I asked this question, I say the special feature in this case is that the anion, the fractionalized charge, cannot tunnel between layers. So it's totally immobile in z direction. So I think that's there are some quasi-particles which are totally immobile due to topological reason in certain direction. But however, this kind of feature are contained in the green function for anions. But creation operator for anion is not a local operator. So this is became trickier. Yeah. Any other question here? Yeah. It's no. Usually we say the field have this feature that at the low energy, the phase space getting smaller. Here is that yeah, you could the thing that the number field depend on the cutoff. Yeah, so there's no way to get rid of cutoff. It's really there's a number of layers. Really, it's really you see the cutoff at the low energy directly.
Isn't that because you're in an atomic limit to a perfectly flat diamond?
The reason is that because the topological order in each layer, even though you allow tunneling between the layers, this tunneling somehow cannot merge them together. This individual layer structure survive at the low energy, something like that. Yeah, but the more formal way is that this is a particular phase that a different size of a system are not connected by product states. You cannot by dissolving product state to connecting the different size. And another way to say those states have no mirror representation. You know, mirror representation is particularly rely on this liquid property. Yeah. So those are some examples. And here maybe some more general picture. Certainly we have this liquid state, which you can dissolve the product states. You know, those are like a gauge theory. You have anions. You have a quantum field theory and mirror representation. And then there's a so-called S-source entanglement structure. Okay, so that is a concept introduced by Schwingel and McGreevy. And so it really says following: in order to connect system with different size, by including product states is not enough. You need to make a two copy of a system, then stacking them, and then you get a bigger size. You know, here I only have one copy of system, but adding product state. Here you need to make a two copy, and then maybe adding some product states to make the same size and to get to the next level. So if you do two copy, that's S equal to 2. So this layered quantum Hall states is example of a S equal to 2 entanglement structure. And so that's one example. So this entanglement structure is a source 2, S2, S equal to 2 structure. Actually, Fermi liquid is this Gablet state. Fermi liquid actually is not a liquid. Fermi liquid is a source S equal to 2D over 2D is a spatial dimension. And the reason for this picture is that the Fermi liquid should be viewed as stacking 1D system. You know, on the Fermi surface, at every point of Fermi surface, I have a 1D system. And then you have a stacking for many 1D system. This may be a better way to view Fermi liquid. And the number of 1D system grows as you make your system bigger. Your Fermi surface in K space have the same size, but the K point getting denser and denser. So you have a more 1D system on the Fermi surface. So here, this really picture to view the Fermi liquid as a stacking of 1D Latinger liquid or 1D Fermi liquid. And this may be a better way to see Fermi liquid. Actually, Schwingel using this picture to study this the Fermi liquid entanglement is turned out to be very successful. And those states have no mirror representation. Okay, what's a cubic code? A cubic code is this. It's No, I'm not so sure what the two. Okay, I kind of forgot, but I maybe there is something like that. So on the face value, so you need to have a two copy, so like a source 2. So S equal to 2 case, like a stacking. But that's not enough. You also need to have this the different. You also need this the source 2. Some. Let me see. Do I make a sensible statement? Yeah, I'm not sure, but so what? But let me say this way. Maybe it's better. Is that so here when you're changing site, you need to include the product states. And think for cubic code, that's what I heard from her, is that you need to add this source 2 state to get to next level. You know, you adding product state do not bring you to bigger system. You need to add some kind of source 2 entangled state to get to next level. So this is I didn't have reference. You know, Har have studied this the entanglement structure of his cubic code, some kind of bifurcation of entanglement structure. So there's another way. So this is just another way to say how they entangled. So basically, I try to say that this S source is very simple, but the cubic code is even more complicated. So the actually entanglement is in higher dimension can be quite non-trivial. It's very interesting. So yes. Yeah, in 2 dimension is liquid, so the S equal to 1. Yeah. Yeah, the reason in 3D when you scale the system, when you have a bigger system, the number of layer increase. But however, this number layer cannot be changed by dissolving product states. So you cannot by adding product state to get bigger system, because your bigger system have more layers. And so this connection using product states is became impossible. And then, but that's not what we mean by 3D quantum Hall states, because when we say 3D quantum Hall is thermodynamic limit, we do change the layer. The density of a layer do not change, but the number of a layer do scale. So that's the main point. Yeah. Yeah.
So for the source 2 thing for
I think there is something here. Actually, the Grothy DNS is changing wildly for Haas code. For different binding units, it's changing wildly. And yeah. Yeah, that's right. They are not equivalent. So what I try to say, you probably need to add another source 2 state to connect them. Yeah. But this but I put this here. I just want to say that I don't understand this very well. But just to say, there is something beyond the S source picture. S source picture is easy to understand, but even that is not enough. There's a more complicated entanglement structure. Yeah. And so then there's a fermion. So far what we considered here are really only apply for boson system. You may ask why, seems what you say is very general, why you say your definition only apply for boson system. And the reason is that the definition for local unitary, this unitary operator are different. So when I say in the boson system, when I say local unitary, I really means that some operator only act on the sub-Hilbert space on those sites. So those operators really act on those on-site Hilbert space. So that's what this local unitary operator means. But however, for the fermion system, we allow, when for fermion system, this local unitary actually is not local at all. They can act on any states. Then you say, then what do you mean by a local box? There should be some locality in the fermion system. So this became very, very delicate. So for the Fermion system, what we really have is that this local unitary operator for the Fermion system, this box, actually representing something like that. There's something construct using Fermion operator on those sides. So say like UIJK act on IJK is construct using Fermion operator on the I side, J side, or maybe K side, you know. But however, the operator construct using those Fermion operator on those side is not the operator act on those subspace, because the Fermion operator have these strings. When you do Jordan-Wigner transformation, have these strings go over all the system. So when you represent as an operator, those operators are non-local at all. It's not the operator act on those IJK side. It may have a string cover half the system. But they commute, you know. But the IJK and I prime, J prime, K prime, they do commute. But so it is this shuttle definition, because Fermion operator itself is non-local. So therefore, this local unitary box is not a local operator in the boson sense, but they do commute for different boxes. They do commute. So local in that sense. So therefore, here I want to emphasize that in the Fermion system, we secretly change the definition of this local unitary. So therefore, this local unitary equivalence are performed using a different class of so-called pseudo-local operator. So when you're changing that definition, so therefore the classification, the mathematical problem all became different. So this is so that's why the Fermion have a different formulation. Yeah. Okay. This also working in higher dimension. Maybe let me put it this way. Fermion operator is operator which unlike commute when they're far away. So certainly that operator is not local. But however, we ask the following question. Suppose we have two Fermion operator, Ci, Cj. So those Fermion operator kind of commute when they're far away from here. Then you ask, do you have a local operator representation of a Fermion hopping operator? The answer is that in one dimension you have, in higher dimension you don't have. So although those Fermion operator commute far away, there is no local operator representation of that. You have to use something like that. So here we just order the higher dimension lattice in some arbitrary way, and doing this some Jordan-Wigner in that sense.
But then you have long-range interactions of that.
In a sense, the Fermion hopping operator have this very non-local representation. But from algebra point of view, they do commute when they're far away. So the algebra of a Fermion hopping operator determines the Fermion spectrum. So that looks local, but there's no local operator representation. So the higher dimensional Fermion system is rather strange. Their operator algebra looks local, but there's no local representation.
The property that breaks down is that in 1D you can map Fermion system with our ordinary notion of locality.
Yeah.
So that part breaks down. You can still do the transformation.
Yeah.
Sure, but all of the other definitions require locality of that.
Well, but it works with this definition of locality.
Yeah.
It's just different.
Yeah. So what I try to say is that actually this is very, very important. To define a system, giving the Hilbert space is not enough. You need to give a definition of a so-called local operator. And for the Fermion system, the definition of local operator are Fermion hopping operator. This nearby neighbor hopping operator is my definition of a local operator. Then I say that the Hamiltonian are made by those local operators. The so-called local correlation function are again made by those so-called local operators. But when you're looking more carefully, you find the local operators are not local. There's no local representation in the bosonic sense. Bosonic sense, local means you really act on the subspace. But for the Fermion, there's no such representation. But your definition of local operators sounds consistent because they commute. The faraway operators do commute. So that's a short. So So basically, this really a question. So what do you mean by a Fermion system physically? What is a Fermion system? I think this may be the essence of Fermion system. There's an operator algebra which looks local, but the lack of a local representation is a true meaning of a Fermion system. So in that sense, the Fermion green function is not a correlation function of a local operator. Fermion operator is not a part of my local operator. Fermion pair is a part of local. So Fermion green function have a pretty strong power of detecting topological order. But that's not a correlation function of a local operator. And so actually, for the topological order, if you compute the green function from anions, they probably have a similar power for Fermion green function. But however, for the Fermion, like topological insulator, if you really consider correlation function with local operator, they probably have nothing. These are two-body correlation function may have nothing. You don't see anything. Yeah. 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 Yes. Yeah. They are bosonic. So they do braiding, they're bosonic. So they looks like they should have a bosonic, some local thing, but they don't. Yeah, it just don't. So because this feature, sometimes I will try to say that there's no way to bosonize a Fermion system in higher dimension. If what you said is doable, then you can really map the Fermion system to boson system. And here really means that they are truly different in some very intrinsic way. Yeah. Okay, yeah. Yeah, in one periodic boundary you have same thing. So actually the Jordan-Wigner mapping only for open boundary condition. So for periodic boundary condition, you cannot map the two together. Yeah. Okay, so here I just give some example. And what is an example of long-range entangled states? Certainly here you heard a lot of examples, so I'll just quickly go through this. And here one point is that when you have an equal weight superposition of all particle position, that's a boson condensed states. So that's a superfluid. The superfluid actually is a product state because the equal weight superposition of all particle configuration can be written as a tensor product of a state at a position z. Z is a spatial point. Where at the z point we have a linear superposition of no particle at the z, one particle at the z, two particles at the z, and etc. When you span this, you probably get all kind of combination. So that is so actually superfluid states is somehow closer to product states, And but how to make this superfluid state, which is a product state, to have a long-range entangled, to be long-range entangled? One idea is to scramble the phase. So actually Laughlin states is following this idea. We scramble the phase. So now we say that it's still superposition for all particle position, but we have very non-trivial phase. So this ZR minus EGA, this phase factor is the phase can change wildly. So that's one way to scramble the phase. So when you scramble the phase, you have a good chance to get some topological ordered states. So but here I scramble the phase I write this in some very special way. I write this this wave function ZR minus EGA actually is a wave function for field Landau level. If you field one Landau level, you get this wave function. That's a Fermionic wave function. When you square that became symmetric, so it became bosonic wave function. So therefore, the filling function 1/2 Laughlin state is like a square of a field Landau level wave function. And so that's one way to scramble the phase. And then we can there's another example for spin system. That you have this spin up field Landau level and spin down field Landau level. So you have a fermion, spin up, spin down fermion. Then you put this wave function on the lattice. So that z would now become discrete, no longer x plus iy coordinate. Z became discrete. Then you also do one more thing, is that you enforce constraint that there always a 1 electron per site. So then this wave function became wave function for the spin system. When you one electron per side, it became a spin system. So actually, this wave function actually is the so-called chiral spin liquid. I think Donna Sheng probably talked about that in his lecture last week. So this is another example for a topological order in the quantum spin liquid, which is written down quite early. And then there's then we can play the game. Here say you square the wave function of a field along the level, singly field along the level. Well, here we can square a wave function with two fields along the level. Why not? So here this chi2 is a filling fraction 2 quantum Hall state with two along the level field. Then you square that, you get another bosonic wave function. It turns out that this wave function is very interesting. This wave function is a bosonic non-abelian quantum Hall states. It have this name called SU2 level 2 quantum Hall states. And so they certainly can make this into Fermionic wave function by multiply anti-symmetric wave function, which is one field along the level. You can always do that. Actually, this is like a similarity transformation. When you do that, these two states are very similar. Maybe their abelian statistics change a little bit, but non-abelian statistics do not change. So there's some very similarity between the two. So there's for every bosonic non-abelian state, just multiply this factor, you can get the Fermionic non-abelian states. So this is one of filling fraction 1/2 non-abelian quantum Hall states. And then there's another thing is that you can then follow the similar trend here. You can put electron superconducting state on the lattice. You have electron superconducting states. You put them in the lattice. Then put a constraint with 1 electron per site. Somehow magically, this wave function became a so-called Z2 topological order. Again, this is the one of early construction of topological order, which is different from chiral spin state. So that again, this again for the quantum spin liquid. So they call the Z2 spin liquid. So later I will try to explain this. And so maybe let me just skip this because it's been explained by Xie, and maybe Nick Reed described it. So actually, these Laughlin states have a topological order, and there's a generalization of that to multi-layered case, so it's called the K-matrix states. And you have this Z capital I is the electron in different layers. From the different layer, you can say like electron in the same layer on ith layer, they have a power of KII. Then electron on I layer and the J layer have a power of KIJ. So those different exponents can be put into the K matrix, and so you can use the K matrix to construct this multi-layered wave function. The reason I present that is that this is a pretty generic construction for this kind of U1 Chern-Simons term. This is a multi U1 gauge field coupled together with the same K matrix. So therefore, this kind of concrete many-body wave function realize this particular U1 Chern-Simons theory. And this Chern-Simons theory have a special meaning is that every abelian quantum Hall state or every abelian topological order in 2 dimensions have this form. So they're kind of universal construction of all abelian topological order. And so again, this is kind of probably yeah. So then there's if a K matrix have a diagonal element, if all the diagonal elements are even, then this wave function is symmetric. So this kind of K matrix really classify the bosonic abelian topological order. If one of a diagonal element is odd, then actually this wave function would contain fermions, and then that kind of K matrix would classify a fermionic abelian topological order. So therefore, for abelian topological order, using this K matrix state, we have a pretty systematic understanding. So that's one of earlier result for the systematic understanding. And so I think now, so that's kind of a quick summary. So now I'll try to maybe go slowly. So now we have this state is this chi2 square. why this state is non-abelian? We claim this state is non-abelian. You say why? How do you argue that? So the way to argue that is using this projective construction. So here it's more general. We say we have a K field along the level, then square that. We want to claim this state is non-abelian. So how to do that? We view this wave function as a product of two wave function. The square is just write them separately. And view these two coordinates as independent coordinate. If these two coordinates are independent, then it's like you have two kind of particle, like a parton. It's like a cutting electron into two parts. You have two partons. So one parton have a K field along the level. The second parton also have K field along the level. And then we glue two partons together to get back to the electron. Means we do the projection. So we say Zi1 and Zi2 always equal. So like glue them back. So we cut them into a half, then have the two integer quantum Hall states, then glue them back like making projection. And so we use this kind of parton way to view this wave function. And using this kind of point of view, then there's a Slade-Boson approach, which developed in this paper in the early days, high TC. So then one can obtain the low energy effective theory of this wave function. And from low energy effective theory, we can try to guess or conjecture that this state is non-abelian. So that's kind of a idea how to argue this state is a non-abelian state. And so here's more detail, and here is a little more generalization. I raise so we fill K lambda level, but we raise to n power. Okay, so that's we split electron into n partons. Okay, and so each parton fill K lambda levels. And this projection means that we want to tie parton together by identifying all these parton coordinate. But before we do this projection, we just have independent parton, each fill lambda level. So then we know what is the effective theory for that. We just have this. Okay, so this psi I is describe each i's parton. So this Hamiltonian means we say assume parton independent, so each parton have its own Hamiltonian, they see their own magnetic field. Okay, then we assume parton have certain density, so they fill certain lambda level. And then the ground state, so this is a ground state of this kind of independent parton Hamiltonian. And so then what do we mean by projection? The projection is following. Then we realize that to obtain the real electron wave function, there's one particular way to obtain this wave function by saying that we have a Fermion electron annihilation operator. Remember, these electron annihilation operators are really product of many parton operator because electron are bounces many partons. So we just annihilate all the electron. So then to go to annihilate all the particles together to then have an overlap with 0 particle states. So this became amplitude of this wave function. So I write this electron wave function, this wave function in this particular fashion, starting from parton integer quantum Hall states. We have a product electron annihilation operator annihilate all the electron, overlap with 0. This happened to be exactly this wave function. Okay. So why I do that? When you do that, then you can see one feature is that this electron wave function is actually unsinglet. Because in the independent parton model, this I is summed. This Hamiltonian have SUN symmetry. You can rotate between partons, so have SUN symmetry. So usually in the independent parton model, their excitation have a SUN, have all kind of SUN representation there. But this picture really tells you that after projection, electron part only contain SUN singlet. For the ground state, for the excited state, so therefore, this projection really project down to SUN singlet. So this really picture to us to argue that. So projection to the SUN singlet is a way to combine parton into electron. So that's one important point. Yeah. But how do I project? But here the projection, not global projection, because this is a local projection. So locally, every local region is SUN singlet, not globally SUN singlet. It's a local SUN singlet. But the local SUN singlet, there's a field theory way to do that by including the SUN gauge field, by couple the parton theory to the SUN gauge field. Then we have a belief that integrating out the SUN gauge field is performing this projection. So that's a kind of a mathematical way or hand waving way to do the projection. It's like including the SUN gauge field. So now we have a parton theory seeing a uniform magnetic field, but also see this SUN gauge field. And then now we can perform some kind of a field theory trick. So usually we would integrate out SUN gauge field first to go back to the Fermion electron theory. But here we don't do that. We change the integration order. We integrate the parton first. We will integrate the parton first. Parton just form a quantum Hall states. When you integrate the parton first, you just get Chern-Simons theory of the gauge field. Not only Chern-Simons theory of a magnetic field, but also Chern-Simons theory of this SUN gauge field. So when you do this, when you integrate the parton, you get this SUN gauge field. And there's a level K here. This K is almost like a Hall conductance. Suppose this SUN gauge field is like a U1 element, it's diagonal element. Suppose this SUN gauge field coupled to all the parton equally. And then because the parton field K along the levels, so the Hall conductance have a K, is linear in K. So this coefficient would have linear K dependence. So this same feature is there for non-abelian gauge field. So there's a K here. So then this became the so-called, this K is called the level K SUN Chern-Simons theory. So actually that is a non-abelian theory. So this is a typical non-abelian gauge theory. And so there's a lot of field theories out for this Chern-Simons theory. So that then refer that we say, okay, this Chern-Simons theory have non-abelian statistics, then this wave function have a non-abelian statistics. And that's it. So that is kind of our argument. And certainly, it's really the argument, a very hand waving. But it's pretty simple, you don't need to do any calculation if you believe, So there's a lot of belief in it. But certainly, if you want to be rigorous, large in limit, this kind of approach became controlled calculation in large in limit. So when n is very large, and then this became a controlled calculation. Okay. So how do we get non-abelian statistics? Okay, so here I try to have some kind of argument. Oh, yeah. No, this, here it's a way of construction. You can certainly assume, here I assume parton form integer quantum Hall states. You can assume parton form some kind of fractional quantum Hall state and do the same thing. Then you get more general states. That's okay, yeah. Here I just have a particular construction. I just assume parton form integer quantum Hall states. And I think that's maybe interesting topic. You can assume parton form fractional quantum Hall states, then what do you have? Or parton form non-abelian states, then you get new non-abelian states. So you can play all the kind of game. So that's what after high TC, all this parton construction give you all kind of states. If you believe, there's infinite possibility here. So here I want to describe a little bit more detail how to see the non-abelian statistics in the Chern-Simons theory, or maybe in this construction. And So so here I consider example is that this square is a psi k square. You have a k field along the level, then we just square that. Okay, and so let's see. Okay, this red one is like a spin up pattern. Here I'm using spin language. The blue one is a spin down pattern. We have two lines, means we have two fields along the level. This is first along the level and second along the level. Okay. And so here is a picture for the let me see. Okay, for the charge one hole. Okay, yeah. So certainly this is this wave function is a bosonic wave function. So we ask the following question: so we can remove one boson, create a hole. What this looks like? When you remove one boson, you actually remove two partons. So here I remove spin up parton from the top lambda level and remove spin down parton from bottom lambda level. And then we kind of glue these two waveforms together by doing projection. Then this is a picture just describing a hole which have a charge 1. It doesn't have a spin 0 because this is a spin up, spin down. Spin 0 is a projection, because the physical states has a spin 0. Okay, so this is a hole. Okay. However, we can make this fractionalized by moving these two partons, separate them. So now one parton is at position X, another parton at position Y. Let's just separate them. And then do projection. And then here you can see that you have something with charge 1/2. Now you immediately have charge 1/2. And but somehow spin 1/2. Okay. And you see, when you do local projection, it should be gone. I don't know why, but somehow actually when you do local projection, actually they are not gone. Actually this wave function when you bind pattern together is non-zero. So somehow this state did survive the projection, but roughly speaking, this like a spin 1/2 and this like spin 1/2. But this is but spin is hard to describe here. But let me say the charge 1/2. This is for sure. We have two charge 1/2 particle, and this is like a fractionalized particle. This is a hole, just a hole. It's not fractionalized, and these are fractionalized. Okay, so that is a one way, and this particle is supposed to have non-abelian statistics. How to see that? So one way to see this is the following: is to consider situation we have two pairs. So here I only describe one pair. So this blue one and the red one. I have another pair for red one and the blue one. So I have 4 such fractionalized particle here. Then we ask the following question. For the independent parton, how many states do we have? After we fix number for locations, before we fix those locations, how many states do we have? It's pretty simple because each parton is like a spin 1/2, So each one have a doublet. So we have 4 doublet. Okay, and when you have a 4 doublet, put them together, we can fuse this 1/2, 1/2 to get a 0 and a 1. Fuse this 1/2, 1/2 to get a 0 and a 1. Then fuse this 1, 0 together. Then we get those so many states. So totally we get this maybe 16 states. Yeah, we get 16 states here. But certainly some of those 16 states certainly is wrong because many of them have non-trivial spins. They are SU2 carry SU2 quantum numbers, and after projection, only the singlet survive. Okay. So therefore, for among those 16 states, if you perform projections, actually only 2 states survive. Only 2 states survive. So only these 2 zeros, only 2 zeros survive. So this became a very interesting situation that you have a 4 particle where their location totally fixed. But somehow there's 2-fold degeneracy left. Yeah. After projection, you still have 2-fold degeneracy. So it looks like this 4 particle totally have a single qubit degree freedom. 4 particles have a single qubit degree freedom, just 2-fold degeneracy. Just have 2. That sounds like a marijuana, but this you need something along that direction. Okay, so this is the picture. And but however, there's yet another layer of a picture. Is that using this picture? Actually, this picture is very helpful to computing how many states are there after projection. And but however, in this picture, I'm using the spin 1/2 fusion, using the SU2 fusion, because here you can see I combine spin 1/2, treating them as a SU2 representation using the fusion rule of SU2. But however, for our case, the SU2 fusion rule should be modified. Why it should be modified? It's the following. Suppose we fuse these 2 spin 1/2 together. We fuse them together. Okay. When we fuse them together, we get a charge 1. Okay. But the charge 1 have 2 pictures. One is this picture, that spin up, spin down. That's a spin 0 picture. But for the independent parton, you could have also this picture, where the both partons are in the spin up. So I have 2 spin up together, give you a spin 1 component. So this is a spin 1 picture. Okay. So therefore, when you fuse 2 spin 1/2 together, you may get a 0 or 1, a spin 0 and spin 1. So this is this picture, spin 0 and spin 1 channel. But however, this spin 1 exists only when k is bigger than 1. Because if k equals to 1, we only have 1 field along the level. There's no space to put the 2 spin up in 1 field along the level. So there's a truncation. This is a hand-waving argument. I already know the answer to this truncation, so I want to use this picture to argue this truncation. So this really say that if for low level, when you do this fusion, certain high spin is truncated, do not exist. At least if k equal to 1, then this fusing 2 1/2, you don't get 0 and 1. You just get 0. The 1 is truncated. And this one is kind of do not exist. So that's a modification. So in the full representation, that's for the SU2 fusion is from S1 minus S2 to S1 plus S2. Here with this modification, which k minus S1 minus S2, taking minimum of this, so these have a truncation like that. So if k equal to 1, S1, S2 equal to 1/2, then this is 0. So therefore, you can only have a 0 here. So therefore, when k equal to 1, this kind of fusion is modified. So 1/2 only give you 0. And 0, 0 only give you 0. So therefore, when k equal to 1, after projection, these 4 particles only have 1 state. There's no 2-fold degeneracy. So this is really how we explain why k equal to 1, this is abelian. There's no degeneracy associated with non-abelian statistics. So this is a kind of simple way to explain is abelian. Then for k level 2, then for this particular case, they all survive. So there's a 2-fold degeneracy. But however, when you have a 6 particle fused together, then you reach higher spin, then you see the truncation would affect the computation. So for 6 particle for level 2, you would have a less degeneracy than just fusion spin 1/2 computation. And this degeneracy is a sign of non-abelian statistics. Is that even when you pin down the particle location, you still have a degeneracy. And this degeneracy it's kind of spread between those particles because they cannot be viewed as internal degree freedom of each particle. And for some reason, they kind of spread out. And this is a simple way to compute the degeneracy with how many particles. And so that's a way, again, not a full calculation, but I did convince ourselves, yeah, this wave function is a non-abelian. And have this particular SUN level K non-abelian statistic, yes.
If K is bigger than 1, you always get something from 0.
That's right. So when K greater than 1, this is always non-abelian. But the K equal to 1 is really abelian. Yeah. The Chen-Simons theory is yeah. Yeah. The Chen-Simons theory, yeah, actually I don't know how people can do this in Chen-Simons. For the Chen-Simons theory, basically you let me describe a computation, but I myself never did that computation. This in the sense, suppose for the SU2 case, then you can view the SU2 representation as a particle moving on a sphere, you know. So therefore, that's like internal degree freedom, like a particle. So so basically, you have a particle here like spin 1/2, but internal degree freedom can be viewed as sphere moving on this some small internal sphere there. And this particle moving on a sphere couple each other via the Chen-Simons term. Because these are spin 1/2, belong to SU2 representation. So they couple like an SU2 charge to the Chen-Simons gauge field. So when you integrate the Chen-Simons gauge field, you obtain, so you have 4 spheres with particle moving on 4 spheres here. But all those degree are coupled to each other via this Chen-Simons gauge field. So you have the coupled system. And suppose if you do the calculation, compute the coupled system, compute this ground state of this 4-sphere situation, this quantum mechanical problem, you're supposed to get these results. These results, supposed to get these results. And I think field theory people may have a smarter way to do the calculation, but I think for the if you want to do a straightforward calculation, it's really like that. Yeah. And there's another way to see the non-abelian statistics to study edge states. So actually, it's a pattern construction tell you what is edge states. And it's very naturally and very easily. And since people went through lecture of conformal field theory, so actually this is one of the application of conformal field theory. So the picture goes like this. You know, before the projection, we just have independent parton. So independent parton, and for each parton, we have a field lambda level. So this is just one picture of a field 1 lambda level. So if for one parton, this parton field 1 lambda level, then on the edge, this parton would have an edge state. But this parton is a fermion. So their edge state just a 1D chiral fermion system is like this. So those are just a 1-dimensional fermion system where this M is like angular momentum, but also can be viewed as momentum along the edge. So therefore, this is like a dispersion relation. This horizontal axis is like a momentum, vertical axis like energy. So the dispersion relation, then this field theory for this fermion point is this kind of chiral fermion theory. But we have many of them because for each parton, we have a K field lambda level. So each parton give you K chiral fermion edge states. Because when you have K lambda level, you have a K edge, different K chiral fermion level. So, and also we have N partons. So each parton have a K. So total we have N times K chiral fermions on the edge. So that's for the independent parton model. So this N times K fermion are labeled by two index. Alpha goes from 1 to N, label different parton. A go to 1 to K, label different lambda level. So basically, before we do projection, edge state is very simple. Just have a chiral fermion theory. That's very, very simple. So all we need to do is do projection. But in one dimension, it's easy to do projection because of the following conformal field theory results. You know, in this one-dimensional system, we can have a U1 symmetry, which is a total Fermion numbers like U1 symmetry. And this is U1 quantum number. So you can call U1 currents, or you can call U1 density. That's the same thing. So this operator means U1 density, some bosonic operator. And this model, you can do the rotation in alpha. So that's SUN rotation. So therefore, you have SUN symmetry here. Then you have associated SUN currents. So have this case can be written as this. So it's an SUN current. Similarly, you can do the rotation of among A. That's SUK rotation. So that's here. Oh yeah, this is SUK is here. Yeah, this is SUK, this is SUN here. So and then you have those bosonic operators. Okay. Then so what? Well, those bosonic operator in some sense can be viewed vaguely can be viewed as this raising and lowering operator in an oscillator. In the oscillator, if you know the raising and lowering operator, you can generate all the excited states. Here we have something very similar, using those bosonic operator which depend on the space. So Jx, for this Jx for the different x, you can start from the ground state. You apply Jx, Jy, Jz. Apply them many times. You can create the states, excited states. And there is in conformal field theory, somehow they can show that this three current exhaust all the excitation. Basically, you can using this three current operator to generate all the excited states and exhaust completely. But however, they are not quite oscillator. For U1, they are actually really the oscillator. For SU1, SUK, they are similar to oscillator, but the algebra have some modification. It's not quite like oscillator algebra, some modified algebra called the Moody algebra. So, but the idea is similar. You can generate all the excited states. So therefore, we can view this Fermion theory as this boson theory. We have a theory with a three current. This three current generate everything. So it's like a kind of bosonization, and it's called a non-abelian bosonization because we have the SUN, SUK boson field. So we can view the Fermion theory as this non-abelian boson. And in this kind of non-abelian bosonization, the projection is very easy to do because this is the part is for SUN. Just throw away this part, and you do the projection. So therefore, after projection, the projection really means that all your excited states are generated by this U1 current and SUK currents. And SUN, we just throw them away. Okay, and that's it. So therefore, after you do the bosonization, you separate the SUN part. Then you just remove the SUN part. Then you do the projection to SUN singlet sector. So this is really the projection into SUN singlet sector, just dropping this. And both of these two sectors are SUN singlet. And that's it. So when you know the conformal field theory, those are pretty standard in conformal field theory, then you can get that. So therefore, edge state, you have a fewer degree freedom on the edge. There's so-called central charge. The central charge basically is like counting how many degree freedom on the edge, with normalization such that a chiral fermion have central charge 1. Okay. So this theory have a chiral central charge k times n. It's k times n. Okay. And after projection, the chiral central charge is getting smaller because you have smaller, less degree freedom. So here's the results. This combination have a central charge 1 times this. So actually, for large k limit, so this kind of this n k squared, so this k cancel out, so roughly k times n in large k limit. Yeah. But for small, this is less than k times n, so this is some reduction here. So central charge is usually this is not integer. So therefore, the number of edge branch is a kind of fractional. It's not like how many branches. It's like can be fractional branches. You don't know how many. So this again, this typical feature of a non-abelian quantum Hall state. The number of edge branch is not integer. Some fractional branches. So So actually, again, if you believe and using this conformal field trick, it's pretty easy to obtain this result. So therefore, it's a so at the beginning it sounds quite magical, this kind of wave function, it's hard to say what is the property of this wave function. But actually, when you do this field theory calculation, this is a pretty easy state to understand. Yeah. So any question here? Yeah. So this basically is a kind of introduction of this one example for non-abelian quantum Hall states. Okay. And actually, this example we can generalize. This can be generalized. Okay. And so one generalization is to consider this wave function. So this wave function is like a kind of like a double layer system. Naively like double layer. So Z is one layer, W is another layer. So each layer we have a Löffling wave function. So like a double layer Löffling wave function. Okay. However, this S make them into a single layer system. This S means that we symmetrize among Z and W. Between Z is already symmetrized, between W is already symmetrized. And this S means symmetrized between Z and W to make them a totally symmetric wave function. Okay, so this is another weird wave function, symmetrizing this double layer. We're symmetrizing the Z and W to make a double layer wave function into a single layer wave function. So this is basically is something, we do something like that, yes? The chi2 square is different. The chi2 square is chi2 is a two-field lambda level. Yeah, so that's filling function 2. Here, we only have one lambda level for each parton, and the filling function is less than 1. It's 1/2. So this like this is really like we assume parton in the fraction quantum states. But also, we do not do projection. In other words, we do not make a Z equal to W. Here, we just symmetrize among Z and W. So Z and W still separates. We just symmetrize. So actually, here what I say is we want to have a wave function which is have a lot of sum. It's not just a single product. It contains many sums. So we have a wave function containing many sums. So this is the one way to write down this kind of many-body wave function. Okay, and so then we are facing a similar question. So what? Now you have a many-body wave function, and so what is the low-energy effective theory? Is this state an abelian state or non-abelian states? So we can ask similar question. So amazingly, this wave function can also be constructed using parton, understood using parton construction. And so here we introduce 4 partons. Okay. And then this Zi, this Löffling wave function is obtained by using 2 partons. So this psi 1, psi 2, we're using the parton construction to identify their coordinate to get this 1/2 state. So these 2 give us this Löffling states in the usual way. And psi 4, psi 3 and 4 give us the second Löffling wave function. Okay. And then why we do that? Because if you do that, we can say that before we do symmetrization, this wave function just can be written in this way. Have the electron in one layer, electron in another layer, but both written as a product of a parton. So we can get that. But writing wave function in this way, we can write this symmetrization in algebraic form. And here is the magic. Is that we introduce this kind of electron operator. It's a symmetrization is the Z parton and the W parton just add them together. Just add them together. So this is our electron operator. And then we insert the electron operator here. So then we expanded. There's a lot of different summation, different terms. And each term gives you something like that. But there's a sum with different permutations. And that's basically performing this symmetrization operation. So therefore, this symmetrization can be done at the operator level very simply by simply say my electron operator have this kind of combination. not just a product parton, but also contains sums. It's have a product, also have a sum, and that's it. So this is still belong to kind of parton construction. So why I say that? Because of the following. If you view those psi are complex fermion field. So we have 4 of complex fermion, but 8 Majorana fermion, 8 real fermion. So you can do this isolate rotation among these 8 Majorana fermions, or real fermions. Then you can do some algebra. You find that if you perform this isolated rotation, then there's ISO 5 subgroup such that this HZ, this psi E is not changed. So this psi E is ISO 5 environment, is singlet. That tells us what kind of projection should we do. So if you do this parton theory, we have ISO 8 transformation. We should project out this ISO 5 subgroup. So we should couple the parton theory to the ISO 5 theory. So here here I'm just writing down formally. I should really using the Majorana fermion to write down this theory. And this A field is really ISO 5 gauge field, performing this ISO 5 projection. Okay. And there's ISO 5, I think is pretty simple. It's just there's 8 Majorana fermion. ISO 5 just transform among 5 of them. There's a 5 of them, transform among 5 of them, making this E invariant. Okay. And then then you do the same thing. You integrate now each parton have field lambda level, because this wave function each parton field 1 lambda level. You integrate this parton again, you get ISO 5 transformation theory. So therefore this wave function is described by ISO 5 transformation theory. Yeah. So basically all those kind of things. This what you do in last century. So this certain edge states are also simple, because we have on the boundary we have I shouldn't say Dirac fermion, but Dirac really means a complex fermion. What I really mean is complex fermion. So on the edge you have 4 complex fermion. That means 8 Majorana fermions. And when you do ISO 5 projection, you kill 5 of them, and 3 of them survive. So the edge state of this is 3 Majorana fermion. Yeah. So that's the edge states. It turns out that there's a very nice mathematical identity is that this symmetrization of this wave function is equal to this wave function. And this wave function is a Pfaffin wave function. The first part is like a pairing, the POA pairing, and multiply this to some kind of Joshua factor. And this is a Pfaffin state proposed by Moore and Reed. So actually, this wave function is another way to do Pfaffin, And the Pfaffin indeed have a chiral central charge on the edge state is 3/2, because one from this U1 charge mode, and 1/2 is this neutral mode is 1/2, and here also 3/2. 3 Majorana fermion is also 3/2. Yeah. So this is a way we can get Pfaffin states. Yeah. So basically, this is like some kind of review and summary of this projective construction. The reason I introduced this is that the projective construction is actually still very powerful, and I think nowadays people use this less. But I feel it's still very powerful and still worth to learn, and maybe using this to construct many examples of non-abelian quantum Hall states. And certainly, in the Michael's lecture, you learn using fusion category, you can construct a big class of non-abelian states. And this is another way to construct a big class. And actually, this kind of construction have some advantages that the resulting quantum Hall states are easier to obtain in the following sense. It's easier to see what kind of mechanism led to this kind of non-abelian states. It's easier to see. And why? For example, So in next lecture, I will try to say how to get these states. There's a mechanism to get these states. But to finish today's lecture, let me just say, what is the mechanism to get these states? Okay. To get these states, then you'll notice that when you raise this this k field on level raised to the nth power, this wave function actually live in some lambda levels. This wave function not in the first lambda level, but somehow they don't spread out to infinite lambda level. They only live in first a few lambda levels. You can figure out how many. I think it's a number of lambda level is like maybe it's a k minus 1 times n. That's a number of lambda level they live in. Okay. And then you can design the dispersion relation of electrons such that these first few lambda level are totally degenerate. You can design the band structure to make that happen. Lambda level not evenly spaced. The first few are totally degenerate. Then you have a lambda level gap. For this kind of integer lambda level structure, then you have a delta function repulsion to enforce the nth order 0. You can see this wave function have nth order 0 when you bring two electrons together to enforce its nth order 0. Then that's it. Then you realize this wave function. So this wave function is very natural when the first few lambda level are degenerate. Then we have a short-range interaction. You just very naturally get these kind of non-abelian states. So therefore, to achieving these states, if you can engineer a situation where the first lambda level are degenerate plus some short-range interaction, this kind of like a Loftlin states in a situation where first few lambda level are degenerate, then this state will be as natural as the Loftlin states. So therefore, this kind of projective construction usually led to this easier to understand mechanism. And so one can try, maybe one can design some system to realize this kind of non-abelian states. Okay, I will finish here. Yeah. Oh yeah. What? Or realizing these particular states? Yes. You design first. You like in a continuous and not in a lattice. So you have a energy like a k square, a k to the 4th power, and k to the 6th power, 8th power. Then you fine tune those coefficients such that the first a few lambda level are degenerate. For example, this like a chi2 square. Maybe let me say for the fermion, let me just looking at these particular states. I think this. This state. Oh. Okay, these states. These particular states stay in the first 3 lambda level. This particular state. So therefore, you need to fine-tune 2 parameters. Like you have k square, k4 square, and k6 square. Fine-tune these 2 parameters to make first 3 lambda level degenerate. Then you add the delta function interaction among electrons. Then that's it. Then you get these states. Delta function interaction. Maybe not delta. For the electron, you need a V3. You need some short range interaction. Not delta, because the fermion wave function always have 0. Delta function is not effective. You need some short range interaction. And then this wave function has 3rd order 0, just like Loftlin states. The Loftlin states have a 3rd order 0, but in the first lambda level. This is a wave function with a 3rd order 0, but in the first 3 lambda level. If the first 3 lambda level degenerate, and these states will be dominate. It's not Loflin's dominant. These states will dominate. Yeah, and so by fine-tuning this the dispersion relation, you can make first 3 lambda level degenerate. So that's an engineering part, and it's easier than engineering 12 about the interaction, as I just say. Yeah. Yeah, you know the shift. I don't know offhand, but you do know the shift. Yeah, and you mean on the sphere? Yeah. I don't remember, but you can compute the shift. Yeah, it's known. And so if you want to numerically looking for those states, those shifts will be very important. Yeah, it can be. Yeah. So there's a question here. Yeah.
Yeah, you're at definition of local unitary.
Yeah.
That actually
Yes. That's almost a definition. Maybe not definition. So in condensed matter, we say the same phase means something which can be adiabatically connected. So you need a evolution. You know this local unitary evolution. Some evolution generated by the local Hamiltonian. Okay. I think there's a quantum information result. Every local evolution is a local unitary circuit. Yeah, I think no one use that results with all kind of bound and this very careful what kind of bound arrow or definitive arrow, then one can do that. And so then one can equivalent using quantum circuit language. Yeah, but in condensed matter, the definition phase using the evolution, the smooth connection. Yeah. Yeah. Oh yeah. I don't know exactly what to say. If you want to, all these states, I described these states are in the, for example, this kind of wave function or this kind of wave function are for the continuum. You can put this wave function on the lattice. Then on the lattice, then you can say one particle per side. Then you can get maybe not one particle per side. One and zero particle per side. Then you can get this a lattice theory. Yeah. Oh no, the lattice theory also non-abelian. Oh, I see. Yeah, this is okay. Yeah, that's certainly possible. You can see. Suppose we believe this wave function is a topological order, but this is probably easy to say. That's just a two integer quantum Hall states. That's something. And the concern is that when you put this wave function on the lattice and put this one electron per second constraint, you do some dramatic change to the wave function. There's no guarantee that this kind of change may causing phase transition. You actually not in the liquid phase, maybe in some kind of a crystal phase, some ordered phase. All this can happen. This is a very good comment. So all this is possible. This kind of thing can happen. So the argument I present here is assume all those phase transitions don't happen. And but however, there's a way to test that if this effective theory, we have this SUN gauge theory. And so if this effective theory is a semi-classical or weak fluctuating, then that suggests that this SUN projection is more reliable. However, if this effective SUN gauge theory is a strongly fluctuating, then things like what you described may happen. So this projection, when you do projection, you may destroy the liquid state. You may get a crystal states. That may happen. So basically, there are certain limit. What I described is a controlled approximation. I didn't discuss that, but already you can see here. You can see in the large K limit, if K is very, very large, then that's the transformation theory is more or less semi-classical. So actually this suggests that this derivation is more reliable in a large K limit. And so probably there you can do the controlled calculation that this projection is under control, don't destroy the phase. And but however, for small k, like k to 2, this actually essentially really say that this A have a large fluctuations. And this A may causing some dynamical change of this parton, and the parton may form a Wegener crystal, or something like that. So that would be the concern. And here we want to say that although we want to do the projection, we want this projection to have least damage. We want to try to keep this integer quantum Hall state of partons. Each parton from integer quantum Hall state. We want to leave that intact. Hopefully this projection do not destroy that picture. Yeah, but they potentially they could destroy that picture, and that may causing troubles. And when you're putting system on the lattice, you do additional projection, so there's an additional channel to make things not working. Yeah. Mirror. No, this one have a mirror because those are liquid. Liquid state all have a mirror representation. Oh, you say this chiral states. I believe chiral state have a mirror representation. I believe that. And I think what we don't know or what we don't have is they don't have a tensor network representation. No. That's a non-liquid. I'm sorry. Yeah, that's a. I'm sorry. I'm answering a different question. Yeah. I'm sorry. So in this sense, that the liquid always have a mirror representation because the different size are differ by product states. So in the mirror representation, like a different layer of a mirror, they differ by the product states. So that's coincide with this kind of normalization picture. But however, for non-liquid states, the non-liquid state different layer are not differ by product, they differ by something more dramatic. And so that means those states don't have a mirror representation. Yeah. And the state don't have a mirror representation also can also say it's a theory with no quantum field theory, beyond the quantum field theory. Yeah. Okay, I think just finish here. Okay.